So we are here for lecture 14 on the course Proof Complexity as a Computational Lens. We started talking about proof complexity last time, space complexity, and we'll continue. We did talk about proof complexity also last time, but in particular space complexity. And we had this idea now of a refutation or any derivation as being a sequence of active clauses or clause configurations, if you wish, which are the clauses you want to have in memory. Or these could also be, this will generalize later to polynomial calculus to cutting planes. In fact, we'll sort of implicitly use that generalization today later. So what's the idea? The idea is that we start with something empty. When we end, if it's a refutation, we should have derived contradiction. And then how do we go from one configuration to the next for all time steps between 1 and tau, which is the end time? We can do one of three things. We can do an axiom download, which is just that CT is CT minus 1 union some axiom in the formula that we're trying to refute. We can do inference, so that CT is CT minus 1 union some D. D are inferred from CT minus 1. By, well, if we're doing resolution, it's going to be the resolution rule. If you're doing polynomial calculus, it's going to be linear addition or multiplication. What we're going to do today, in fact, you will notice if you pay attention that there's a kind of a semantic version of these configuration style proof system, where you just say, well, the only thing I really care about is that D is implied by the previous configuration. So you can call this semantic resolution, and then you can talk about semantic polynomial calculus, semantic cutting planes. If you pay attention, everything that we do today will actually work in this setting, which is a good thing. You can sell it as that this means that our results are much stronger. As we'll see, it's also a problem, actually. We'll talk about that in a few minutes. And then we have erasure, which just says that, well, we have removed a bunch of clauses. And you can, then there are flavors of whether do you allow to erase only exactly one clause, or here I allow you to erase several clauses in one go. It's not so important. If it ever would make a difference, then I would pick whatever suits me. Right? So this is how we now define resolution or any proof system, where the length of a derivation, as we talked before, will now be the number of axiom download plus inference steps. And then the space is, we have three measures. We have clause space, we have variable space, and we have total space. We're going to focus on clause space, but let's make sure to define all three. We can define them for a configuration. Clause space is just the number of clauses, and we just write space. This is somehow the main measure that we care about. We made this choice. Variable space of a configuration is just the number of variables in it, counted without repetitions. Total space is counting with repetitions. So take all the clauses in this case and sum up their weights. All clauses in C sum up their weights. Okay, and now if you let M be any space measure, then we do the obvious thing that for this pi now, the the m measure of pi is just going to be the max over all configurations in pi of m of the configuration, right? Where m now is total space or variable space or closed space. And then for a formula m, the m space of refuting the formula is just the min over all refutations of the m space measure of the refutation, right? Nothing surprising, hopefully. Okay, so what did we learn last time? So suppose that we say, just to make results slightly cleaner to state, whenever it suits me, I'll let f be a k-CNF formula. And unless I say otherwise, I think of k as a constant over n variables. Then what did we learn last time? Well, we talked about the worst case. Oh, and f is unsatisfiable, because otherwise it's not so fun. The first thing we learned was that the refutation clause space is linear in the number of clauses, also in the number of variables, except for some additive constant. So this already tells us where the somehow the range where the thing is going to play out. When we're proving space lower bounds, we're going to be between constant and linear. Is the way to think about it. Or at least the worst case measure of space is linear. We learned that clause space is an upper bound on width. And this is up to an additive constant, actually, for k-CNF formulas, where the additive constant will depend on k. The space of refuting f is an upper bound on the width of refuting f. And this means that we can basically ignore all the papers that proved space lower bounds for pigeonhole principle formulas, for random CNF formulas, for shaping formulas, because we can just plug in our width lower bounds and immediately get these results. This is not how they were discovered. So basically, first all the space lower bounds were proven, and then the pattern was spotted, and then that series Dalmau showed this general result. And then we said that there's a strong trade-off between space and width. We said that there are formulas of linear size with a linear number of variables and clauses, such that they're very easy with respect to both width and clause space. Constant. In fact, we got the constant 3, which is kind of best possible, but for which it held for any refutation of these formulas, we had that if we looked at the clause space of that refutation and the width of that refutation and multiplied, then we got n over log n, except for constant factors. So you can achieve best case for both space and width, but that will force the other measure into essentially worst case behavior, because also for width, obviously, if you have n variables, then the worst case width is n. So except for constant factors and except for a log n. I think that's basically where we were last time. What else? How did we get this last result by Ben-Sasson in 2009? Well, we looked at pebbling formulas. So what are pebbling formulas? we have a directed acyclic graph with fan into with a single sink, something like this. This is a pyramid of height 2. This will then generate a pebbling formula for every source node. Every node we identified with a variable, and we say that the sources are all true, so U, V, W are all true here. And then for all non-source vertices, we say that if the immediate predecessors are true, then the successor is true. So not U or not V or X says that if U and V are both true, this forces X to true. Not V or not W or Y says that if V and W are both true, this forces Y to true. Then not X or not Y or Z says if X and Y are both true, then Z is true. And then we make the formula contradictory by saying that the sink is false. And we claimed, and remember, we also had this pebble game where we could place black pebbles on a vertex if there were pebbles on the predecessors, and we could remove black pebbles at any time. White pebbles was the opposite. We can place a white pebble at any time, but we could only remove it if the predecessors were pebbled. And we were interested with these rules for black and white pebbles. How few pebble placements do you need, and how few pebbles do you need in total to reach, go from an empty graph to a graph that is empty except that I have a black pebble on the sink. And the way we got this trade-off result was to say that any resolution refutation of a formula like this can be translated to a black-white pebbling of this graph with like the same properties with respect to time/size and space. I didn't say exactly how to prove this, partly because I was thinking about giving this as an exercise, but at least I meant to give a hint. So let me try to give the hint since I forgot it last time. So the idea is as follows. So we start, the claim is take any resolution refutation of a formula like this. Here it is. Up to C tau, which contains contradiction. And what I'm going to do is I'm going to construct from this. So from every clause configuration CT, I want to construct or extract the refutation, a pebble configuration of black pebbles at time t and white pebbles. Okay, and I'm going to do this somehow, and then I'm going to take all of these together. And then I want to argue that this is a valid black-white pebbling, and then I'm going to, the formal claim is that the pebbling space of this is going to be the total space of this refutation, or total space as defined over here. And then actually the pebbling time is going to be upper bounded by the length here. Even something more precise can be said. The number of pebble placements here is going to be upper bounded by the number of axiom downloads. Note that again, I won't actually care about the inference step. So I don't really care whether you're doing syntactic resolution or semantic resolution here because I'm not counting inference steps anyway. You'll get them for free. Okay? How do you do this? So the idea behind the translation is that if the positive literal V for a vertex V is in some clause in CT, then I will add V to the black pebbled vertices at time t, V sub t, always. So positive literals, then I consider them to be black pebbled vertices, always. Otherwise, if I have a negative literal in CT, then I will add, I will consider V to be a white pebble vertex. Okay, so now I definitely have now we can look at this refutation. And this is going to give me a sequence of pebble configurations. It's not a valid black-white pebbling, but I'm saying you guys will be able to fix it. Okay. So maybe to see this, like suppose I start by just downloading not u or not v or x. Okay, then I have a black here and a black. Then I immediately get a black here, which could make you nervous. But I also get two whites down here. So the way to think about this, like this appearing immediately should be okay because I think of, maybe I place these first and then placing that one was okay. And note that whenever I download an axiom, that is always what will happen. The only reason I wouldn't get a white here is that there's already a black there from before. Right? So this should be fine. And now maybe I download, in fact, let's see how that happens. Maybe I now download X or not X or not Y or Z. Then Z should be black and Y should be white. And you realize that, yeah, this also, and X doesn't change because it's already black. So I don't want to do anything. And this is again okay because this guy was black. This is white. So then I can place a black pebble there. Now maybe I resolve them over X. And now I get U, not U or not V. Or what do I get? Not U or not V or not Y or Z. And then maybe I erase these two guys. Okay. Then you see that this looks okay because the only thing that happened here was this. And now you can continue in this way. And I'm going to argue that you see, except we needed to somehow figure out in which order am I placing the pebbles and so on and so forth. But things are going to work out. It's my claim. Except for there are a few things. You will note that what t tau, what will that be? Well, that will be the empty configuration, which I didn't want. I wanted a black pebble on the sink. But you do, looking at this formula, you realize that it's minimally unsatisfiable. So in particular, I am downloading the pebbling axiom. These are the so-called pebbling axioms. These are the source axioms, and this is the sink axiom. So I am downloading the pebbling axiom for Z at some point because the formula is minimally unsatisfiable. So I'm not refuting it otherwise. So let's just agree that as soon as I do this, at that point in time, as soon as I do that download, I will get a black guy on Z. Okay, let's just keep it there. I mean, we're talking under 2-1. Okay. Two other things that I will need is things will break a little bit. Suppose I, just out of spite, suppose I just downloaded not X or not Y or Z, and then I immediately erased it. Now you're in trouble, right? Because then I would have, first I get white, white, black, that's fine, but now all of these just disappear. That's not fine, because that's an invalid removal of the whites. But then you can say, yeah, but that's stupid. Before you remove this guy, you should have resolved it at least once. If you downloaded it, you have to resolve it. Otherwise, why would you have downloaded it in the first place? So let's make this formal. Okay. And also, another thing that you can say, well, as soon as you've resolved over the clause for the last time, remove it immediately. Why should you keep it around? It's only increasing your space. Okay. And now my claim is that we do this fix for the sink, and we do pre-processing of the resolution refutation to disallow it to do stupid things that are just annoying to us, and now it's going to work. Do you believe this? Okay. Hopefully you somewhat believe it. And I was going to give it as an exercise. Already last time we saw a number of open questions And I tried to argue that I think these are good open questions that someone should solve. Now today we'll talk about a few questions that are not so open, but are still very natural, I think. So the first thing is that we know it follows immediately from if the space is an upper bound on the width, it follows in particular from this that if the space complexity is constant, then the complexity of refuting f with respect to length is polynomial. And now the way to think about this, how do we compare width, length, and space? Well, width and space scale between 0 and linear. Length scales between 0 and exponential. So somehow, to get a fair comparison, you should sort of compare length to the log of the the space and the width, you should sort of compare it to the log of the length. Then you have them in the same kind of range. And this tells me then that if you're easy with respect to space, then you're easy with respect to length. Is the other direction true? So suppose that, and again, I'm just to make this cleaner, suppose that these are k-CNF formulas. Suppose that the length of refuting a formula is polynomial. Does that imply that the space of refuting it is then small? Say, I don't know, logarithmic or something. There are some asymptotics, big O's here also that you can like, you wish, or at least, so the length is, let's say that it's L, which is poly n, or can we at least do better than space L over log n? This we argued last time that I take this refutation in length L, I view it as a graph, then I can pebble it. I can always save a log factor when I pebble it. So we know that if you can refute in length L, you can refute in closed space L over log L. Can you save more? That's my first question. And there's a question here also.
Yes, so you said that the space should be compared to the logarithm of the length, and you said that when the space is constant, then you have a polynomial length. What if the space now is logarithmic?
Excellent question, and I hope that you will answer for me. This is one of the open problems I mentioned last time. But suppose that the space complexity is logarithmic, then do we know anything? That's all.
Okay, thanks.
So that's all. Yeah. And here in the other direction, I'm asking now, suppose that the length is polynomial. Can I say, can I bring the space down to logarithmic, or at least can I shave more than a log factor? That's question one. Question two, suppose that f is refutable simultaneously in, suppose that f is refutable in length L. There is some proof that does length L. And also in space S. Whenever I say space today, I mean closed space. Unless I'm like being careful, then I mean closed space. Then I can ask, can we achieve these two measures simultaneously? So length L and space S simultaneously. And you can say, well, that's maybe a little bit too much to ask for, so let me, allow you constant factors or something like that. So can I, if the space complexity is S, if the length complexity is L, can I achieve both of these measures simultaneously? We saw already for width that this was, the analogous question was, the answer to the analogous question was no. Question three is a sort of a relaxed version. So suppose that the length of refuting f is L. And you can say, can I, okay, let's just ask a ridiculous question. Can I at least do that in worst case space? Okay. Is it possible to achieve simultaneously length L and linear closed space? Worst case. A very mild question. In fact, let me be even more generous. I'll allow you a polynomial law. This is sort of arguably, if the answer to this question would be no, then the answer to this question is also no. This is a sort of a more fine-grained version, if you wish. And the fourth question, since we have that space is an upper bound on width, since in fact for all the formulas we've talked about so far, space and width coincide, like for any single formula I think you've seen in the course so far, it's natural to ask whether is it really the case that space and width are somehow the same? Okay, let me be generous here again and throw in maybe like an asymptotic vector or something like this, or can they be separated? So I'm trying to argue that these are four interesting, natural, relevant, exciting questions that are well worth spending a couple of hours on answering, if we can. Are you buying this? Questions about these questions? Do they make sense?
You said discussed question before that we don't know anything. I mean, we know that the length will be possible.
No. If you know, you should write it down. I don't know this. No. So let me. Okay, so let me give some spoiler alerts maybe. I mean, we are going to try to use pebbling to answer these questions. This you already guessed, probably. Let's see what some limitations are now. So even here, note that we actually had this question the last lecture, and I asked if the space is constant, can I achieve polynomial length and constant closed space at the same time? And even this, as far as I know, is open. If you have a way of proving that this is true, then I think you should write it up. I don't know this. Note that for pebbling, this is kind of vacuously true. In the pebbling world, this would be true just by counting argument. If my pebbling space is at most S, then how many different pebble configurations are there? Well, essentially n choose S, and there's no need to repeat the pebbling configuration. So if I want more dramatic trade-offs than that, if those are true, then I won't get them from pebbling. Also, any graph I can come up with and translate into a formula, obviously, you can always pebble in linear time and linear space at the same time. Just fill up the graph in topological order with pebbles. So pebbling formulas will never answer this question 3. It will always say, yeah, of course you can do it. Also, we have another problem if you think about it. Remember our configuration style definition of resolution? I said that I don't really care about the inference rule. So in fact, all the proofs we're going to do today, they will work for a proof system where whenever it does an inference step, it just says, it follows semantically, therefore let me have it in a single step. Okay? But then note that semantic resolution can always refute any formula in linear clause space and linear length simultaneously. How? Well, download the formula, that's n steps, stare at it, say, this is unsatisfiable, therefore, I derive bottom. One additional step. Okay, so step length was number of clauses plus 1, space, number of clauses plus 1. Okay, so now you take your pick. Like if you're going to do a size-space trade-off in this model, then of course you're going to sell the fact that you're in the semantic model as a strength of the result. Oh, even if I completely disregard inference rules and allow you arbitrary semantic inferences, the lower bound still holds, which is great. But if we want to answer question 3, this is like really bad news because our model is a bit too strong. But this is the model we're going to work in today. More questions about making sure that we understand these questions?
The semantic model, it doesn't depend if it's resolution or if it's anything.
Oh, no, it does. Good. So what's semantic, like why do I call it? Really, it's the way you should say it's semantic clause proof system. And polynomial calculus will be the semantic multilinear polynomial system. And cutting planes will be the semantic linear inequality system.
But for example, those that deal with the clauses, it's the same.
Yeah, if you like the semantic version and the configuration style, I just care about like how efficiently I can store intermediate information. Yes. So there's, yeah, in that sense, it's like semantic resolution. It's not really about resolution. It's just about that I'm allowing you to store your information as disjunctive clauses. Whereas the corresponding model for polynomial calculus, and I say, oh, I afford you more power now. You can actually store things not just as a set of monomials, but you can also combine them and add them up with coefficients from your field. Okay. So what we're going to see today is that in contrast to Turing machines that, as Ryan Williams told us, can actually get down to roughly square root, this is optimal. Like resolution can never say more than a log factor. Oh, and I see what should I have written here? Can do length OL and no, I said space order. Okay. Simultaneously. The answer is again no. You cannot, so we'll see very strong time space trade-offs or size space trade-offs. You cannot optimize both parameters simultaneously. We'll have to take a pass on this one because we're doing pebbling today. But we'll see maybe hopefully next week that actually even this super relaxed question that I just want you to do polynomial in the best possible proof size. And please just, you don't have to sweat, just, maintain worst case space complexity. That's all I'm asking for. That's asking too much. You cannot do this. But again, sort of inherently, the tools we've developed now, we already argued why they cannot answer this question. And can they be separate? Well, the way I wrote it, are they the same? No. Can they be separated? Yes, in a very strong sense. So we'll see that there are formulas with a linear number of variables and clauses such that the width of refuting these formulas is constant, a small constant, and the space, clause space, will be n over log n. That's what we want to do. Okay.
Good. So,
Yes.
but for this FN that you say for question 4,
Yes.
can't you just take the ones that highlight the trade-off between width and space that you just erased?
No, because then they had constant space complexity.
Yeah, but you said that for whatever proof that you take,
Yeah, but there is a proof in constant space. Here I'm saying these formulas.
Sorry. Yeah. Okay.
Yeah.
Yeah,
So
my bad.
there are constant space proof for those formulas. Those were pebbling formulas, and we saw that if we did a top-down refutation of these, then you could do constant space.
Okay.
So then I want formulas that are dead hard with respect to space. Not just that saying that doing small width and small space at the same time is dead hard, as you already know, but now I want unconditionally. I want to show that just says, yeah. Potentially, like the measures could still be the same, only that you have to come up with two different proofs. But there are always, like, if there's a width efficient proof, then there's always a space efficient proof. You just do the obvious thing.
Yes.
Right? But I'm saying no, that for these formulas, there's a width efficient proof, but space is worst case behavior. How much do I want to raise? Maybe I want to raise it here. So our starting point are going to be, so let me tell you what is known using the fact that, okay, now we're going to use the following. There are lots of results for graphs in the pebbling literature. We do know that black pebblings translate into resolution upper bounds. Resolution upper bounds translate into white pebblings. So there's a mismatch here, except that in the pebbling literature, there are many, many families of graphs where luck would have it that we have matching, like the upper bounds for black pebblings and the lower bounds for black-white pebblings happen to match up to asymptotic, up to constant factors. So if we can find such a graph family with interesting properties, then maybe we're in business. Okay, so throughout now here, all the formulas Fn that you see are going to be 3 CNF formulas with theta n variables in clauses. So let me tell you what is known. And let me also say, just to save typing, that all of the refutations I'm going to talk about now, you can always keep the width constant, because these are pebbling formulas. And sort of, if you're, well, it requires an argument maybe, but okay. I'm just trying to save typing that all the refutations you see here are constant width, because otherwise I'm going to fill up all the board. So the first thing I'm going to claim is that there are formulas such that the length of refuting F is linear, but the clause space, but the variable space, if I can type this correctly, the variable space of refuting Fn is n over log n asymptotically. These are, we talked last time about that there are graphs with worst case n over log n black-white pebbling price. Take those graphs, translate them to formulas, and use the Ben-Sasson the Ben-Sasson only, Ben-Sasson 2009 theorem that I just erased here, which says that any resolution refutation carries over to a pebbling where the pebbling time is turns into the length, and the length of the refutation turns into pebbling time, and the space of the variable space of the refutation turns into pebbling space. So doing that, if I take these hard graphs, turn them into pebbling formulas, run a resolution refutation on them, translate back, then I get formulas that have linear refutations, but the variable space has to be very large. Okay. Another thing we talked about pebbling, that constant space in pebbling means polynomial pebbling time. Right, and now we can ask, what about logarithmic pebbling space? Does that mean also polynomial pebbling time? And the answer is no, in a very strong sense. So basically, I'm going to state it slightly imprecisely, but pick a formula, any function, your favorite function g of n, that is super constant. It can't grow too fast, but we're not interested in fast now. We're interested in slow. Okay, so it's like there's some upper bound m to the 1/7 or something like this. But the point is that you should think of this as inverse Ackermann or something. This is the interesting range. Okay. Then there are formulas for which the following holds: that the total space of refuting these particular formulas is g of n. And you can also do this in constant way. So they're super easy with respect to total space. The length of refuting these formulas is linear. In fact, let me write it slightly differently. So let me write it in this way. Let's see. There are refutations pi n which achieve that the length is linear. Okay, so this is like 2a, 2b. The length is linear, and the total space of these particular refutations is, and now it's going to be ugly. Let's see what we can write. It's going to be linear over gn squared. And let's raise all of this, take the third root of this. Okay, so these are refutations that are short. The total space is still not too bad, except, well, it's fairly large. I mean, it's depending on your point of view. I mean, gn is like nothing, and now I'm taking n over gn and I square it. Well, g squared is still nothing, and then I take the third root of it. So this is gigantic space compared to this. Okay, so you can do them in very small total space. You can do them in very short length, but then the total space goes up significantly. And the point is that if you have a refutation such that the variable space is n over gn squared, 1/3 minus epsilon. So I'm shaving an epsilon off in the exponent. Then the length of such a refutation is super polynomial. Okay, so this tells you, and these comes from pebbling. So even from pebbling, as soon as you take any non-constant space already in the pebbling world, you're in the super polynomial regime. This requires a proof. This is not an easy result.
This omega 1 depends on G, right?
Say again?
This little omega 1.
The omega and the yeah.
Okay.
So, and this is actually one of these papers, I think, where the black, so we need the matching black and black-white results. I think the black-white was missing here, so the black-white was something that I did. The black result is from two early papers in the 80s. The third result that I want to tell you about, just to give a sense of, you're sort of, I mean, okay, so again, what are we doing? We're taking black and black-white pebbling, we're translating them to trade-offs between length and essentially variable space. And you can say, this is not what we want at all, like getting a little bit ahead of ourselves. I would like to erase all the total space is fine. I'd like to keep that because total space is an upper bound on closed space, but all the var spaces, if they could just be, if we can just strike out the prefix var, then we can go home. Right? Because then we would have very strong trade-offs between closed space and length. This is what we want. So let me tell you a third result that we would want. So there are also formulas for which the total space, so let kappa and kappa prime is a constant, kappa is also a constant, kappa prime is way smaller than kappa. So there are formulas which are refutable in space kappa prime times n over log n. So these come from you can think of them as worst case almost formulas with respect to space, but at least kappa prime is pretty small. There exists refutations which are in linear length. They're in constant width that I'm not typing out again. And then the total space linear length. The total space is also linear. Okay, so these are formulas where, well, at least I can do them by doing the trivial pebbling. And now it holds that, well, if you can come up with some refutation so that the variable space is less than kappa n over log n, not that kappa is way larger than kappa prime. So we definitely know that we can do variable space kappa prime because we can do total space kappa prime n over log n. But even if you push your variable space down to that fairly, I mean, this is not a small space, it's just very minor savings, then for such refutation, the length will in fact be exponential for some epsilon. And I'm not telling you the dependencies of all of these. So this is what the correspondence between pebbling and resolution gives us so far when we just do the obvious translations from, again, black pebbling gives us resolution upper bounds. And then we say, so A and B is like what we get from black pebbling. And then we say, suppose that we have a good resolution proof. Then we extract the black-white pebbling from it. And then we hit the lower bound. And that's where this comes from. And now what we would like to do, again, like we would be super happy if we could just get rid of these vars. So the end goal of the lecture is, suppose I can replace this variable space by closed space. Then, in particular, you see that this result would answer question 1, and also since everything is in constant width, it would answer both 1 and 4. And 2 and 3 would give 2 different answers for question 2 in different regimes. And these are just examples, by the way. I mean, if we could get this to work, then pretty much like you hit the pebbling literature, and then you can just translate back and forth for any pebbling trade-off and get the resolution trade-off. So but the challenge is really like, we know now, okay, so far it's all looking very promising, except that we already saw last time that these formulas are dead easy. This is just not going to be, we're not going to get anything from these formulas. Except that the connections are intriguing. So the question is if we can do anything to fix this. And we talked about last time, what would the idea be? The idea that we will use is to substitute every variable here by a function. Some Boolean function for d variables where d is small. And then we'll expand it out. And then we get a new CNF formula. And now we need to argue two things. We would need to argue that suppose we do a substitution with a Boolean formula with a constant number of variables. Is it still true that black pebblings will translate into good resolution refutations? Okay, and the answer is going to be yes, because you sort of do the same thing. Okay, and then we can hope, well, now we can hope for what is in more modern terminology. That terminology kind of wasn't around at the time, but we would be looking for a lifting result. It would be great if we could find a substitution function so that we can lift the variable space lower bounds to clause space lower bounds. That's our plan. And you can do this in great generality. So basically now I would like to, so let me give you an informal definition. I'll give you the definition by example, and then in the scribe note, you can write down all the formal details. It just takes a bit of typing, and I don't want to waste our time on it. So I'll just tell you what it is, and we will trust that we understand it. So we have a CNF formula F, and we're given a substitution function F. And so lowercase f is always going to be a Boolean function for us from d bits. Then I'm going to define f substituted or lifted by lowercase f as the following. So we substitute every variable x by f of x. We substitute not x by not f of x. And b expand out to CNF. And in order for this to work, for every Boolean function, I have to tell you, like, basically what I'm going to do is I'm going to replace x by a CNF encoding of this function over fx1 up to fxd. I'm going to replace not x by some CNF encoding that you and I agree on not f over x1 to xd. Okay, so now I get a formula that is not the Boolean formula, but it maybe contains ands and ors and stuff. And now I just use De Morgan's laws to expand up. And if d is constant, we're going to have a little bit of a blow up. It's going to be exponential in d probably, but again, d is a constant, so everything is fine. Okay, and I'm just going to assume that this is what we get at the end. You could do this for any gadget. Let's, for concreteness, let's do this for XOR, binary XOR. That's a good choice. So let us maybe do it by example and then convince ourselves that we're happy with it. So okay. So suppose let's fix f to be binary XOR, and let's see what happens. Just we'll convince ourselves that we can do not x or y, and once we see how that works, we're going to be happy. Okay. So now the point is C substituted by F is then not x1 XOR x2 or y1 XOR y2, but this is not written in the right form for us. So this is going to be actually, now I need to expand it out. So it's kind of, the formula now will be not x1 or x2. Let me do y1 or y2 first. So y1 or y2 is going to be, well, one of them should be true, and one of them should be false, right? This is what this is. Not XOR is going to be exactly the opposite. So x1 or x2 not, and not x1 or x2. Yes? And now we just expand out, take a deep breath, and we get something like x1 or not x2, or x1 or not x2, or not x1 or x2, or not x1 or x2, or, and then let's work on this side. Here I want y1 or y2. Here I want not y1 or not y2. Here I want y1 or y2. Here I want not y1 or not y2. Okay, so if C is this, then C substituted by F is this. Okay, and obviously now F substituted by F, just take every clause, generate, every clause gives me a CNF formula, string all of them together. Are we happy with this? So again, clearly you have to write down a little bit more carefully like what we mean. We could also do this for other, what are other Fs that we could imagine? One inspired choice would be majority of x1, x2, x3. One other choice that we talked about last time is x1 or x2. This is a particularly interesting choice because there are actually, so my first two papers show that if you take pebbling formulas and you substitute by binary OR, then for complete binary trees and for pyramid graphs like this, you actually get the right space lower bounds. So for instance, if you take a pyramid graph, you generate this formula, you substitute with binary OR, then the space complexity, closed space complexity and resolution of that formula is going to scale like the height, which is square root of the graph size. This we know. So therefore, OR is an interesting function. But a bit of a spoiler alert is that so one of the open questions, we're not going to be able to make OR work. And I don't have a good reason for why this shouldn't work, so this is one of the things you could fix. But we could make binary XOR, we're going to be able to make work. Majority of 3, we're going to be able to work. If then else, the selector function, we would be able to make work. So we're going to give like a combinatorial condition on which Fs are going to be good. So maybe a good place to try to get now is to see. Okay, so we want to work with this formula. Like, why would these formulas? Like, why does this seem like a good idea? Does this seem like a good idea? So let's. What can you even tell me about this guy? Well, okay, one thing that I claim as an easy exercise for you is that F substituted by little f, I will always assume, by the way, that little f is a non-constant function. This is a kind of a non-triviality assumption. You're not allowed to substitute with constant functions because that's no fun. And in particular, a constant function, you're going to have problems representing one of these two. It's not going to end well. Don't do it. So f is a non-constant Boolean function, capital F is a formula. Then I claim it's obvious that this is unsatisfiable if and only if f is unsatisfiable. Exercise, not too hard, believable, yes? Okay, so if someone gave you this formula f substituted by little f and asked you for a resolution refutation, because resolution refutations do exist for unsatisfiable formulas, how would you refute it? Suppose someone actually knew how to refute the F formula. Would that give you some guidance?
Yes.
I mean, potentially, yes, right? You would, what would you do? You would sort of mimic this refutation step by step. Like whenever, okay, so what's the idea? So let's write it down because it's kind of important. How to refute F, the substituted version of F. Okay, so we have a refutation pi of F. And we could just simulate to get a refutation pi sub F of the substituted formula. How would we do it? Well, basically, the idea would be if D is in some configuration CT, then make sure, then we just make sure that D under F, the set of clauses is in DF, DT. Sorry, if D is in, okay, so this is a brilliant choice of letters, but it's too late now to change, I guess. If the clause D is in the clause configuration C sub T, then I just take D and I substitute it by F, and I make sure that all of these clauses are in D, where DT is the refutation that I want to build of the substituted formula. Okay. How will this work? Well, I will get the empty set at the beginning to be sure. At the end, we have contradiction. Contradiction under substitution is contradiction, so that's fine. Axiom downloads. Whenever, if D is an axiom, then these are also axioms, so I just download them. And now you can ask, like, oh, but what if I do D or D1 or X and D2 or not X, and then I get D1 or D2? Well, then I want to do, then by induction, I have all of these clauses in memory and all of these clauses in memory. So by the implicational completeness of resolution, so basically I know that D1 or X under F and D2 or not X with substituted with F imply D1 or D2 under F. Okay. And now just by the implicational completeness of resolution, resolution can derive anything that is implied. So there are derivations of these things. Okay. And now suppose in addition that all of the formulas, this is important, but all of the formulas that we are dealing with, all of the refutations that we are interested in, they're going to have constant width. Okay. Meaning the number of variables here is constant. Note that this implicational completeness comes at a cost. We've seen that implicational completeness in resolution can cost you exponential length. But this is going to be exponential in terms of a constant. Okay. So now I actually claim that we have kind of done the proof that black pebblings are going to be possible to simulate with just loss in constant factors. Are you buying this? Because again, when the refutations that we get from black pebblings, they are going to have constant width 3. So actually, and the factors are not even going to be that bad. Okay. So we will get, we sort of already have them already. We sort of have this, and we will have this, and this part we also have. For whatever substituted F we want, if we plug in the corresponding graphs. What happens in this simulation? What happens to the space? So note that if we look at binary XOR, or if we look at majority or some other function, then we do have a clausal representation of f, and we do have some kind of clausal representation of not f. These are the ones we had down here. Suppose that both of them have more than one clause. Then, in that case, what happens is that the variable space of pi, when I simulate, that will sort of give me, actually the variable space of pi will be a lower bound on the clause space of pi f. If you just sort of do the, you kind of saw this here. Here you have variable space 2, and you see that actually it even blows up to clause space 4, not only clause space 2. So this is a lower bound. So this is looking excellent, right? Okay, except that you say, yeah, but I mean, sure. But why would the adversary do this? I mean, clearly, the adversary knows that we're trying to prove space lower bound. So he or she will do a completely different proof for the substituted formula that doesn't do this naive simulation. Clearly, right? So our claim is going to be that no, that's not possible. Like whatever, basically, so we'll go in the other direction. So let me state an informal math. Then maybe it will be a good time to take a break. Let's see if I can state this informally. Okay, so let me do an informal lemma, and then we'll formalize it after the break. So fix any CNF formula f, and fix a cleverly chosen substitution function. Cleverly chosen binary XOR is going to be clever enough. Majority is going to be clever enough. Binary OR, unfortunately, will not be clever enough, or at least I cannot prove it. Fix pi to be a refutation of f, pi sub little f to be a refutation of the substituted formula. Let them be optimal with respect to variable space and clause space, respectively. Then this is not exactly what we want to prove, but it will hopefully be clear that if we could prove this, then we should be very, very close. Okay, so I'm picking f, and I'm doing a pi, and I'm saying the only thing you need to worry about here is optimize the variable space. Okay. And here I say, for the substituted formula, all I care about is optimize the clause space. Then I'm claiming that if we choose f in the right way, in fact, the clause space of refuting the substituted formula is lower bounded by the variable space of refuting the original formula. And if we can prove this, then very clearly we should be in business. Like if we can do this, then we already have our answer to question 1 that separates length and clause space. And this isn't, so far, this isn't addressing trade-offs because we're assuming we're at optimality. But once we do the proof, we will realize that this will in fact hold for any kind of correlated refutations. Okay. How would we prove a thing like this? So the proof idea will be something like the following. This is not quite going to work, but it's close to something that will work. So we're given a refutation of the substituted formula. And let's, from now on, I think I'm going to try to have the notational convention that whenever you see closed configurations D, they live in the lifted space, in the substituted space. I'm also, and I'm going to translate them. The idea now is that we want to, okay, so here we're going to construct now a pi, which is C0, C1, up to C tau. Now, the indices are going to be slightly off. Just as for pebbling, this is not going to be exactly a resolution refutation, but it's like it's going to be close enough. It's sort of, it's so close that you will see how to fill in the details. And therefore, since it's kind of nice to see that these two line up, I'm going to keep the same indices. Although actually they're going to be like sub-derivations in between here. Okay? And what's the idea? Well, my idea is I'm just going to do a simulation. So, okay, so what would, maybe this is a good question. What would you do? Someone is giving you this refutation, and with excellent poker face just says that I didn't think about pebbling when I did this at all. Like, I didn't think about F. Right? So I have no idea what you're talking about. You believe that this person is lying. The person clearly took some refutation pi and just simulated it. Except for maybe adding some obfuscation steps or something. Okay? But we're just getting this. How would you extract the thing that you know that this came from? Any ideas? I mean, we know we're postulating that it started with a refutation and then they built this, and that's the only way. We just have an extraction. Is the problem making sense?
Yeah.
Okay, except that how do we extract? Well, suppose, I mean, actually, let's do an extraction operation that at least works for, like, what is an extraction operator that would work for what we believe the person did? Yes?
Well, you take the clauses that are supposed to have replaced the variable, place it back to by the variable.
Yeah, okay. So it turns out syntactically won't work.
Yeah.
But let's do something very close to that. Let's say that something like the following. Let's say that I will place C in CT if DT implies C under F. Close enough?
Sure.
Okay. Then we know, okay, let's sanity check. Would this, in fact, if we did our mimicking proof and then ran this extraction, would this work? And the answer is, yeah, I think so. The problem is, will this work in general? Okay, so you can view this as we have like we have two blackboards, right? The lifted blackboard, which exists, and then we have like our original blackboard that we're trying to reconstruct. And at every point in time, like for every t, we just look at what this is, and we study all the implications. And for any implication, we write something down here. Okay, and this will now give us this. And now we want to argue that this is essentially a resolution refutation. If we can pull this off, then we should be in excellent shape. And then there's one formal lemma that we want to say that, again, we want to argue that also the upper bound, like if there was a refutation, if there is a refutation of F that is in constant width, and some length and some space, then the naive mimicking will only pick up constant factors so that we still have the same total space, the same length, except for constant factors. And this is thanks to the refutation width of this particular refutation being constant. And in the notes, you will have this as a formal lemma with even a proof, but the proof just says exactly what we did, like basically derive the clauses one by one. Axiom download is clear. Erasure is not a problem. For inference steps, use the completeness of resolution and use that the number of variables involved in this particular derivation is constant. So you get an exponential blow up, but it's exponential inequality. Okay. Questions on this before we have a break? Yes.
How tight is the bound?
Fairly tight. I mean, we don't have it yet, but I mean, you're saying what will our end result be? I won't state any constants, but it's something like that. So we are going to get the same tightness as the upper and lower bounds here, except we lose like maybe a factor 2 or at most a factor 4. So this is like, and in fact, this is one reason why it would be nice to do this for binary OR is that then you would expect to have actually the constant factor being 1 and just lose additive stuff, which would be really nice for some applications. But for XOR, sort of you're just going to be able, we're only going to be able to prove that every variable sort of has to turn into a clause. And already for binary XOR, you see that that is not tight, right? Even a unit clause, when you do XOR substitution, turns into 2 clauses, not 1. And with majority or something, then you get a larger blow up. The proof techniques we're going to use, I can't pick up this extra factor on top. Not that I killed myself to try, but like I don't know how to do it. That's another good way of thinking. Like, can you somehow squeeze more out of the argument? I'm going to be able to, like, every variable is going to turn it to at least 1 clause. And for XOR, we kind of already see that that's off by a factor 2. And I cannot quite nail that factor 2. Yes?
And the other one, so the explanation you gave kind of works for a generic F, but here your lemma is stated for a cleverly chosen one. So where does that fail for a generic F?
We'll talk about that after the break. So I'll do most of it. Like most of the idea will work for any non-constant F.
Okay.
And then we'll see where you have to be clever is like everything will work except that you need to, the lifting step where you need to argue that, oh, variable space turns into clause space. That's the only place where it matters how I choose mine. Everything else that we're going to do is going to work independent of this.
Okay.
Thanks. Okay. Let's have a break. We're back from the break, and in the meantime, the board has magically filled up with some useful definitions. Let's just say, so we're going to have sets of clauses, and we're going to actually take disjunctions of them. So let me define what that means. If I have a CNF formula or a set of clauses, C, and another set of clauses, D, let's just introduce the notation that C or D just means that you generate all pairwise disjunctions. C in flat style C, D in flat style D, and you take C or D. This is sort of a natural definition. If you're buying this definition, then actually the only thing we need to do is we need to define for a positive and negative literal what F substitution means. This we already did for XOR. And then the formal definition for a substituted clause is that you take the disjunction over all literals for the CNF formulas representing that literal. That is like the formal. And now F substituted, CNF formula F substituted by F is just the conjunction of all of these CNFs. That's the formal definition, no cheating, no nothing. You just have to tell me like how you're going to represent the formula F that you have in mind. For notational convenience, so from now on, we're going to have the original formula F, and let's say it's over variable X, Y, Z without indices. F lifted by F is gonna, so little lowercase f is a d function. So let's just say that those variables are x1 up to xd, y1 up to yd, z1 up to zd. So if you see any variable with indices, they live in the lifted space. Any variables without indices live in the original space. Any d tends to live in the lifted space. Any c tends to live in the original unlifted space. F is the Boolean function we use for substitution. So far, I haven't committed to resolution. Let P be any sequential proof system. It could be cutting planes, could be polynomial calculus, could be whatever. It can be resolution also. I said that D is going to live in the math-cal P space and are going to be, linear inequalities or polynomials or clauses, whatever the proof system P is. C, in the original space, we're always talking about resolution. So let me just tell you what we need from. We already have an idea for projection, right? We talked that we're going to see if the clause set or the set of constraints D, if it implies C lifted by F, then somehow we should recover the unlifted C. I'm going to think about that as being in the lifted space and then projecting down to the original space. So we're going to define functions. We're going to be a little bit more careful than what we just said. It almost works, but not quite. So a projection takes something in the lifted space and projects it down to the original space with clauses. It isn't a projection if it satisfies 4 properties. The first property it should have is this thing we said, that if D implies C lifted by F, then it's not clear that I'm projecting C, but at least I'm projecting C or something stronger. Essentially, I'm projecting C or a subclause of C, potentially. Okay? So that's completeness. Non-triviality is that my projection function should, if I start with an empty configuration, then I want an empty configuration back. Monotonicity is a nice property that if D prime is stronger than D, and if a clause C is in the projection of D, then C or something stronger, some C prime, is in the projection of D prime. That's prime. Okay? And then the final slightly technical property is related to the only time fun things are going to happen is when I download an axiom. So think of A as being an axiom in the original formula. And then it gets lifted to the axiom AF. And over in the P world, where we might have polynomials or whatever, let's say that LA is an encoding of one of these constraints. And suppose that if I have a configuration D, and I add some fragment from the axiom A, but in the lifted space, and suppose this projects C. And now I'm worried because it could be that D, if D already projects C, then I'm not worried. But if D did not project C, then I need to be able to justify why C suddenly appeared. Okay, and the only move I can do here in the unlifted space is I could say, well, maybe it's an axiom download of A, and then I did some resolution steps. Am I making sense? Okay, and this had better work because I can't think of any other trick to pull at that point. So this is I call it incremental soundness. It's soundness with respect to adding new axioms. So I'm saying if the proof that we have in mind is supposed to work, then the following pretty much has to hold, that the only way, if C is in the projection of D union, a fragment of this new axiom, but C is not in the projection of D, then at least I have not A or C for all literals in A, except the ones that are already there in C. They are derivable by weakening from the projection we had before. Okay, if that is true, because then it's going to work, right? Then I'm going to, by weakening, I derive all these clauses, and then I'm just going to resolve with the axiom A, and then I'm going to be in good shape over in my original space. Is this making sense? Okay, but then I claim that with the same settings, if T is a sequential proof system, F is any non-constant Boolean function, suppose that we have any function of this form. We had one candidate already, which we'll have to see if it satisfies this. So then basically my claim is now that if I d0 up to d tau is a p refutation of the lifted formula, then I claim that for CT being the projection of DT, this should be a pi f probably, then I generate the new sequence pi C1 up to C tau. And my claim is now that this is essentially a resolution refutation. Okay, I have to make this clear what I mean. Meaning anything that is interesting in the resolution refutation, you can read off from here. Okay, namely, what do I, let's see, I'm going to say the following, that C0 is the empty set. I'm going to claim that bottom is in C tau. And when you transition from, so in general, going from CT to CT minus 1 to CT is going to require potentially an unbounded number of resolution steps. But you can do this transition in variable space max of the starting point and the end point. CT minus 1 and CT. This is property 1, property 2, property 3. So that means, what does this mean? That in terms of, since we're interested in variable space, right? This is the projected, we're projected down to the base plane, to the original world, where we have variable space rollbacks. And now basically what I'm claiming here is that if you measure the variable space of these snapshots, then that is essentially the space. Nothing fun happens in between. You lose at most a factor 2. Okay. Why do we care about this? Well, because that means that if I can prove now, like getting a little bit ahead of ourselves, what we want to prove now is that if the variable space here is large at some point, then the class space or monomial space or whatever up here must have been large. Okay, and then you could worry, you could say, no, all of these spaces are small and I only maxed out in my variable space in between, and this says, no, that doesn't happen. Like these faithfully measure the space up to a factor 2. And I really want you on board with this. Some of you are on board with this, maybe all of you. And then the fourth thing is that you do an axiom download in this constructed pi only when there is an axiom download in pi f. And I claim we're going to be able to prove this. And this is again, okay, so here is like, let me see, let me sketch this maybe. Let me do the easy part. So the fact that the emptiness maps to emptiness, that's non-triviality. The fact that bottom lies in CT, that's by completeness, right? Because d tau implies the projection of completeness, and therefore by monotonicity, no, by completeness, if d tau implies contradiction under substitution, then that should be derivable by weakening from whatever is projected, but it's really hard to derive contradiction by weakening. Okay, so that means that this is easy, this is easy. This requires a little bit of care, and I was planning to cheat you on this. It's not super hard, it's more like, it's a little bit annoying. But it's not really that fun. How can you tell that you only need axiom downloads when you do axiom downloads? Well, this whole model, observe that it somehow intuitively, if you think about the way we define prediction by monotonicity, we don't really care about the inference steps. So anything that happens in inference steps, I'm just going to do over here by weakening in erasures. And also when I do an erasure, also by monotonicity, I only need weakening in erasure moves. The only time I'm adding new semantic content, that is when this LA that is from an axiom appears. So that's the only time when I could possibly need to download an axiom. Maybe I even won't need it. But if it turns out that I need it, so basically I will look at whatever new clauses appear in the projection after the axiom download. If all C's are in the projection of D, or if they're implied by the projection of D, then I'm fine. Otherwise, as we talked about, this incremental soundness is exactly what I needed, and then I just do one axiom download. So this is kind of, I don't know, maybe a squiggly check mark. You semi-believe that this is. So then I'm not claiming that this is a proof, but I'm claiming that if you sit down for 10, 15 minutes, you'd write it out beautifully, properly. And nothing fun will happen. You're gonna juggle these definitions. Or you say that I'm only going to care about the prediction we actually used. I'm going to tell you in a second, and then you just do it for that. Questions about this, or are we semi-happy, or even more? Okay, but so far we note that this, I didn't use anything about F here. So the only thing I need now is, what I'm interested in is I have a space measure here in mind. For us now, you should think of P as being also resolution, but the space measure here is closed space. Here over on the C side, we're always doing resolution, that's fixed, and the measure is always variable space, that's also fixed. And somehow, the property that I'm after is, I take my CT that is a projection of DT, and I look at CT and I say, wow, the variable space is pretty large here. Okay. Then I want to say that over in the P proof system space, whatever measure that guy had in mind must have been large here. Okay. So let me write down what that means, and then argue that if we can get that, then we're home. So let's say that a projection is space preserving if the following holds. Let me say that it's space preserving of degree k. K is think of it as a small positive integer. The smaller the better. 1 would be amazing. If basically for every D in the P proof system over the variables that exist in that universe, it holds that if I look at the variable set in the projection of D, Note that this is over on the clause space side. Sorry, this is over on the resolution side. These are clauses. This is like in the unlifted space. Okay, so basically, I should write the bar space here. Bar space. Okay. This measure, I want it ideally to, here's the P space of D. It would be wonderful if I had this, but maybe I won't. But I can hope for Q of this for some polynomial Q of degree K. And I should probably say with like with positive largest coefficient or something like this. So now I claim that, okay, so let me say that linearly space preserving, let's see if I can spell that, is when Q is like, you know, some K times N plus K2. Exactly space preserving. Is when Q is actually the identity function N. Okay. So now I claim that you were buying this lemma. Okay. If in addition my projection is space preserving of degree K, then the space bound, I get the space bound over in the lifted space that is a kth root of the space bound, variable space bound for resolution. Do you see why? So again, we just run this projection and we get all of these nice properties that it's a valid refutation. The number of axiom downloads is already correct. And then we just look at, okay, so suppose we have a, let's look at the variable space of pi. It maxes out somewhere. Well, it maxes out somewhere between a CT minus 1 and a CT. So let's look at those. And for those, we know that, well, the variable space is smaller than Q of this. So I just take the Q, I take the kth root on both sides, and then I get that the space with respect to the p-proof system of D is at least the kth root of this. For resolution, we're going to get K equals 1. So no roots, no nothing. Okay, so all I need to do now, if you're buying this, we just need to argue. Now we can forget everything about any proof system. We just need to remember the definition of projection. And I need to argue that the projection is space preserved for resolution. Getting a little bit ahead of ourselves. So I'm going to define it. And what I define, and you could say then I don't know how to prove that this works also for polynomial calculus, but I can say more. I can prove that it does not work, unfortunately. But it's still conceivable that something like this, if you tweak it a little bit, maybe, I don't know, works for polynomial calculus. I don't know. I hope to say a little bit about what we can do for polynomial calculus. Okay, so now we don't think we need any of this any longer. For cutting planes, this will not work for a simple reason. Like, again, what this gives us for resolution now, it's going to give us n over log n closed space lower bounds for super easy formulas. For cutting plane, I spent like a number of the best years of my life to try to prove something similar for cutting planes. And then Galesi, Pudlak, and Thappen proved that actually for resolution, what do you measure? Closes. So there's closed space. For polynomial calculus, the size measures monomials. So the corresponding space measure that we care about is monomial space. For cutting planes, we measure the number of inequalities or the number of lines. So this corresponding measure that we care about is line space. Galesi, Pudlak, and Thappen proved that actually cutting planes can refute any CNF formula in constant line space. And that's a pretty significant barrier to extending this to cutting planes. You can get size space trade-offs for line space in cutting planes. We have done it. We'll hopefully talk about it in January. They're very different techniques. We still use pebbling formulas. There's no way I would give up on pebbling formulas, but you have to do completely different technical stuff. But for polynomial calculus, I don't have any like good barrier results, and except that what we're going to do now doesn't quite work. So I'm going to say that. Okay, so let me say that D precisely implies C substituted by F, if just to have a piece of notation. Basically, the idea is that D does imply C lifted by F, but for every subclause, it's not the case that D implies the subclause. So one wrong thing is like when D implies anything, if you throw that in, you're going to throw in tons of weak clauses and your variable space is going to be gigantic, and that is clearly not what we want. So I'm sort of picking out the minimal Fs, the minimal Cs that should be there. Am I making sense? And now the projection is then going to just be the resolution projection of any D. This could be clauses, this could be anything. That's just going to be all the C's such that D precisely implies the lifted version of C. That's our prediction. Okay. Now, if you're a real sucker for constants, then you're going to do something like the following. You're going to define the localized, optimized resolution projection. And that's going to be, you're going to look at all the subsets of D, and you're going to project them. Because then you're potentially going to project a little bit more. So you're going to get like better constants in your bounds, but I think we're happy with this today. So this is our, if you don't care about the constants factors, then this is good enough. But since Christoph asked about like the exact constants, then you should definitely work this out. Gonna something like a factor 2 right there. Okay. So now I have two things that I need to argue. I need to argue that this is a projection in the first place. And my board technique goes from strength to strength. I had it over here, but I erased it before, even though I didn't need to. But what did we need? We had this non-triviality that the empty set projects to empty set. That's clearly true. We need this monotonicity and completeness, and they kind of follow. They're just saying that, well, completeness says that if this holds, then either I project C or something stronger. And it's kind of clear that either I project this or I will project some subclause, right? And it's kind of clear that if I strengthen D to some D prime that implies more, the only thing that can happen is that I project subclauses instead. And then there's this thing of incremental soundness with axioms. it's actually somewhat interesting, but there are also other things that are interesting, and it's getting a little bit late in the day. So maybe you can work it out as an exercise or something. It works. Okay. But yeah, so maybe I would have actually, I think I wanted to do it, but didn't plan my time well enough. Okay, now but the question is, okay, so this is a projection for any f. Another question is it space preserving? And let me say that f mapping d bits to 1 bit, let me say that it is k non-authoritarian if no restriction rho with domain of rho at most k fixes f. Okay. So there's no small clique of just k guys that can group together and say let's make f true, let's make f false. Okay. It's also k non-authoritarian. It's also known as a robust function, but then I think it should be k plus 1 robust. If you're working with stronger proof systems, like we haven't talked about k-DNF resolution, but this is going from resolution slightly higher in the Frege hierarchy, then actually what we're doing today also works, but then you need, for k-DNF resolution, I think you need k plus 1 non-authoritarian function. We're going to be happy with k equals 1, and let's just say that that's a non-authoritarian function. Okay. What are non-authoritarian functions? Well, I mean, x1 XOR x2, or in general, like if you want the k non-authoritarian function, just take XOR of k plus 1 bits, right? I would argue that the majority of x1, x2, x3 is non-authoritarian. Why? Well, fix any single variable to true or false, the other two guys can still flip the majority. Okay. What about x1 or x2? Well, pick any variable, set true, and now you fix the function. So or is an authoritarian function. That's why I'm not able to deal with it. Except for binary trees and pyramids, we can, right? But in general, somehow it's messy. So now my claim is, here's like our punchline, and here's what's missing. So if f is non-authoritarian, so one non-authoritarian or true robust, then the resolution projection with respect to f, I missed that index here, is linearly space preserving. Okay. Does the statement make sense? Okay, so basically what I'm saying is what we need to prove is you have a bunch of clauses over x1 up to xd, and you apply this thingy, and then you look at you get a bunch of clauses over just xyz variables, and you look at how many variables there are, and you're saying that, well, that must be a lower bound of the number of clauses in here. How would we prove this? I struggled with it for quite some time. So it's, but at the end of the day, it turns out that, remember we did this proof for minimally unsatisfiable formulas where we somehow set up clauses on one side, variables on the other, and then did some Hall's theorem kind of thingies. We'll try something similar. We'll have to be a little bit more careful, but okay, we know what space preserving is now, I think. So let's see if we can do the proof on this board. What do we want to say? So here we're fixing any D, and let V star be, well, we take the projection of D with respect to F. And let that, so these are the original variables without indices, right? X, Y, Z. And we want to prove that we want to show that the number of clauses in D is greater equal the number of variables in D star. Okay? So without, so let's make some assumptions. Let D be minimal such that we get this. I mean, first I look at what V star is, and then let me throw away all the clauses I can from here. I mean, clearly that's only decreasing the number of clauses. So you're fine with this? So I'm saying now that we know that D implies a bunch of clauses such that their variable set is this. If I remove anything from D, then the variable set shrinks. Okay? In particular, are you with me then that there must be some clause in here and that will disappear when I remove something from D? I mean, some variable disappears. That variable was in a clause. Yes? Good, because we're going to use that later. Pretty soon, I think. So now we're going to do a bipartite graph. Here we just have actually the clauses in D. And here we have the variables in D star. Note that these are like constraints in P, but we fixed the proof system P to be a resolution, so there are clauses here. And I am, so this is X, this is Y, this is Z. I'm going to draw an edge if this clause contains any one of those, that they are not over these variables, but they have like X1, X2, X3. So if any Xi appears, we get an edge. Something like this. Okay. And the neighborhood. So now the neighbors of these four clauses over here is this, right? So we use the same neighborhood relation as before. One thing that I'm going to need is that n of D is V star. By the way, I defined it here. The only way I can pick up X or Y or Z here is that there is some Xi or Yj or Zk over here. Okay. Why is this? Well, this is because of this minimality condition somehow. Like, if truly there is no Xi in here, then I would shrink the clause to remove the X and I would still be fine. Are you buying this? So this is, I'm sort of claiming that this is true, and I kind of told you. Okay, so actually, I know that this maps to this. Okay, fantastic. What do I want to do now? Okay, now fix D1 maximal size such that that D1 is larger or equal the neighborhood of D1. Okay, here it seems that I think this is going to be D1. How do I know that D1 exists? The empty set seems to work fine, right? So, plug it in. If that's the largest you can get, and if you can get something larger, then take something larger. But fix it, it's maximal. Okay. So, if it so happens that D1 is equal to D, then we're done. So suppose that D1 is not D and set D2 to be D minus D1. Here's D2. I claim that there exists some C in the projection such that D1 does not project C. Oh, let me also, let me see. The neighborhood here, let me call it V star 1. Let me call everything else. Oops, this looks a little funky. Let this be V star. Okay. You agreed with me that there is some clause that is not projected by D1, by minimality, right? Okay, so let's C be C1 or C2, where Ci is over V star I. Okay. Now, certainly, okay, I was a little bit sloppy. It should not is also okay. Let me. I also don't want it. I claim that there's a C such that D1 doesn't project C, and also it doesn't project any subclause of C. So basically, because again, V star shrunk, so pick like a minimal clause that contains V star. Because now I want to say, basically what I'm claiming is now, what do we get? We get that D1 union D2, by definition, oh no, maybe I don't need that assumption, let's see. It's definitely the case that yeah, I don't think I need that assumption, maybe. It's definitely the case that all of V implies the clause C, because it is projected. But D1 does not imply C1F or C2F. And it also, right, because if it did and it projected something sharper, then actually this would also project something sharper and C wouldn't have been a clause. Are you with me? Buying this? Okay, so but then in particular, definitely, I mean, let me even remove this. I mean, definitely D1 does not imply C1 over F. Good. So hence, fix alpha 1 to vars D1 star such that alpha D1 is true, alpha C1 over F is false. This I can do, right? And clearly, I mean, alpha is only assigning these variables. Now, there are some things that I note that I didn't draw quite the right picture. We could actually have things like this also. I think that's going to be okay. But what I do know now is that I do know that there are definitely no edges from here. There are no edges from D1 to V2 stars. There could be edges from D2 to V1 star, and this makes me a little bit nervous now, because alpha 1 is like, I'm not exactly sure what it's going to do to these guys, but we'll get there. Okay, so now I claim that if you look for every U in D2, look at the neighborhood of U intersect V2 star. What can you say about the size of the neighbors? I claim that this is larger than U. And probably strictly larger, even. Why? Well, if I could find two vertices here that only have one neighbor in V2 star, what would I do? Well, I would add it to D1. Yes? Okay, so for any subset I consider here and I look at the neighbors here, the neighbors over here are at least as many as this. Does this sound useful in any way? Like there could be a matching, maybe, if we talk to Uncle Hall. Okay, so there's a matching. Let's fix it. Like maybe this. So there exists a matching M from D2 to V2 star. But that means that every clause in here contains a unique variable. Like this variable is, this contains, I don't know, x1, this contains y2, etc. So I can, so I set matched variables in vars D V2 star to satisfy D2. So now, so far I have satisfied everything here. I've also satisfied everything here. I have falsified. Okay, so let's see. What do we have so far? This is satisfied. This is satisfied. This is false. I'm not so sure about this. But at least this guy was not affected by setting the V1 variables, because, I mean, it doesn't mention those. It is affected by these assignments very much. But f is a non-authoritarian function. And I only assigned one variable per group. So now what I do is I extend to falsify C2, sorry, that's not a fat C, C2 lifted by F. How can I do this? By non-authoritarianness. But now this is also false. Contradiction. So it can't be that D1 is less than D. So these clauses are as many as these variables. Are we happy with this? And now, so now we just go back to what I had on the board before, and we strike out var in all of these amazing theorems. And now we have huge, and also we can do this for other pebbling results. And now we have like a rich collection of trade-offs. We also have separation of clause space and width. And I should say that this is, so what you've seen so far is basically my PhD thesis. So this is what I did. And these two papers that I presented now, that's joint work with Ben-Sasson. The space width separation is 2008, and then we did the trade-offs in 2011. It took a while to get published. And if you want to optimize parameters, probably binary XOR is the best substitution function. Then you get 6 CNF formulas with all of these properties. And then you can think about, like, can you turn them into 3 CNFs? Probably I didn't have the energy. But it's except for, when I do the XOR substitution, I pick up a factor 2. I pick up any factor in the pebbling trade-off, but many of these pebbling trade-offs are like really, really tight. So these are tight results in the sense of many of them have asymptotically matching upper and lower bounds, which is kind of nice. So question, open problem 1, can you do this for polynomial calculus with the similar machinery? Okay, question, that's like open question 1. Open question 2, can you at least prove for pebbling formulas that the monomial space is lower bounded by the black-white pebbling price? I don't care how you do. Can you do? I think the intuition is that this should be possible. So now I want to say just that, sorry, this is one of these lectures that are going slightly longer now, but I've done a few short lectures, so maybe hopefully that is okay. So a few quick observations. Fix the proof system P to be, say, polynomial calculus resolution or cutting planes or something like this. Cutting planes. And let's use our R-proi definition, resolution projection. Let my substitution function f be the identity. I don't substitute. Okay. Now, if you just look at the definition that I, again, very conveniently erased, I'm really going from strength to strength, you will realize that it's not so hard to see that by our definition, it's actually, this is exactly preserving when you map cutting planes variable space to resolution variable space, or when you match polynomial calculus variable space to resolution variable space. Why? Well, because of this argument you had, if a variable appears in some resolution clause, The only way it can appear is that it was in some constraint, because otherwise you would have trimmed it away when you minimized your projected close. Am I making sense? Okay, but that tells you, you take any CNF formula F and you run projection, that if you have a cutting planes or polynomial calculus proofs in some variable space, you can translate it to a resolution proof in at most the same space, yes? We just proved this. It's a very funky application of our beautiful big machinery, but it definitely works. Okay, but now in the other direction, obviously, polynomial calculus can simulate resolution space efficiently. So what did we just prove about variable space? That it's a measure that is independent of the proof system. Variable space is the measure of variable space. Okay, that's interesting. But that means that what can I say about the variable space in PCR of pebbling formulas? Then, if I plug in the Gilbert-Tarjan and Paul-Tarjan-Celoni graphs, well, seems like I would get n over log n. And now I claim that for PCR and polynomial calculus, I would argue that the total space of any refutation is upper bounded by the degree of the refutation times the monomial space of the refutation. Are you buying that? Okay. The total space, I look at all my monomials and I look at their degrees, and this is like how many literals I'm going to pick up. But that means that exactly this width clause space trade-off that we had for resolution, we could automatically get that there exist formulas Fn such that the monomial space of refuting it is equal to the degree of refuting it, which is constant. But for any particular derivation, if you take the degree and multiply it with the monomial space, that's n over log n. Okay, and this is already, this is like a very simple observation, but this is something that we wrote down in Nordström. Suppose that you take your favorite pebbling formula. Okay, so, but I should say that some things that we don't know. Okay, so here are some things that are open. Is it true that monomial space of refuting F, say it's a k-CNF formula to make this, like, is this at most the degree of refuting F plus some constant? We don't know. But we will try to kind of, hopefully next week we'll see you can actually put a square root there, and it's true. But that square root probably shouldn't be there. You could also ask whether it's true that the monomial space is at most the size of refuting F divided by log size. But now you realize that actually the argument with graphs and pebbling doesn't work, because the nodes now have monomials and potentially several monomials. So this is actually false. And we can find formulas that have linear size proofs, but where the space complexity is also linear. But unfortunately, these tend to depend on the characteristic, which is not so nice. So suppose that you do now in polynomial calculus, suppose you do XOR2 substitution. And now you do the random, and you get a proof in some size and some monomial space. And I hit it with a restriction that for every variable x picks either x1 or x2, and it sets it to a random value. Okay. Then I claim that suppose that x1 is in a monomial M, but x2 is not in M. Then the probability that M row is zero is zeroed out is a quarter. Or let's say that it's not zeroed out is exactly 3/4. Because maybe I don't choose, I choose x1 with probability half, and then I set it to the right value with probability half. Suppose that x1 and x2 are both in M, then the probability that M survives, I claim is a half, which is less than 3/4 squared. Why? Well, I'm definitely setting one of them, and now I have a 50% chance of setting it the right way. Okay. So, in particular, the probability that any monomial is not zero is less than 3/4 raised to the degree. Okay. So, but what this means, and I'm running a little bit out of time. Let me just try to, are you with me? Like I'm just lifting with XOR, and now I'm hitting this with this random restriction. What do I get back? Like the original pebbling formula, the vanilla pebbling formula. But so I start with a refutation of the pebbling formula with XOR. And let's say that it has size T, capital T, and monomial space S, lowercase s. And you hit it with a restriction. Then you realize that if you just do the math, there will be a restriction. I mean, we will get a refutation of the original formula. The size is still going to be at most T. The monomial space is still going to be X. But the degree now is there will be a restriction such that the degree is logarithmic in T, just by doing the math. Just by you pick the degree to be large enough, and then you just do a union bound. And so basically you're going to plug in log T there, and you're going to union bound over all monomials. And if you pick your parameters correctly, then with probability, the probability that some monomial survives is going to be less than 1, so there is a good restriction. Thank you. Okay, but that means that now we can actually plug in the Ben-Sasson thing and observe that somehow with variable space we really don't care. So if G now has, what's going to happen basically is that if it has a pair of black and black-white pebblings in time T and space, you can black pebble it in time T and space S, but not simultaneously in time little o of t and space little o of s, then for this formula, substituted pebbling formulas, they are now going to have, so polynomial calculus or PCR can refute them in size big O of t and monomial space, or total space even, big O of s simultaneously. Simultaneously. But by our restriction argument, it's not possible to achieve size little o of t and monomial space little o of s, but then we have a log t loss simultaneously. So this is by a random restriction argument, I bring everything down to variable space and total space. But this loss is really annoying. And this in particular means that for polynomial calculus, I will get no unconditional space lower bounds. I will get all the trade-offs that I have for resolution. I will get them, but I pick up a log t factor here. So when we're getting exponential, this is going to, get uncomfortably large. But in the smaller range, we have a number of trade-offs in small range where this is going to be fun. But basically, what I would really like to do, there's like no reason why this factor should be there. Okay, and just a final comment, that what does this mean? So I don't get space lower bounds, but what I can prove to you, look at this pyramid graphs again. Okay, one of two things must be true. Either there are square root n space lower bounds in PCR, right? Either you have to believe that either that is true, or pebbling formulas over pyramid graphs have the amazing property that when you go to polynomial calculus and you do an exponentially long derivation, then there are clever ways of saving space. So they have some hidden amazing trade-off properties that we cannot see that manifest themselves not in resolution, but for polynomial calculus. And in fact, we have the same for cutting planes. If you put a polynomial bound on the coefficient sizes, so you're allowed to do cutting planes, but only with polynomially large coefficients, then again, for some version of pebbling formulas over pyramids, I can prove that either I can prove a square root n lower bound, then I think I get like a 4th root n lower bound or something like this, which is either a conditional, unconditional line space lower bound, or else pyramid graphs, pebbling formulas over pyramid graphs have amazing time space trade-off properties for connecting. So I think it would be really nice to solve these sort of problems. So the nicest one, the one where I really think that you have everything that you need, except new clever ideas, is that, or at least I cannot, like I gave you everything I have except the clever ideas, that do what we did today, but do it for polynomial calculus. Show that there is this two-way correspondence from black pebbling to polynomial calculus. That is already clear. What we don't have is from polynomial calculus back to black-white pebbling. And then get the same type trade-offs to work. Or explain why this fails to hold. Right. So, any final questions?
Yeah, could you explain this inequality that the total space is at most a degree times the monomial space?
Because the total space just measures every configuration, and I look at in that configuration what variables are you mentioning with repetitions. So you have like, your space is something like, here's one polynomial. And then here turns out there's a monomial. And here is a third polynomial. Okay, and now I'm gonna just sum up all of these variables with repetitions. That's the total space. That's the case in any proof system. Okay, so now clearly the number of monomials, that's the monomial space. And then I just take the worst case degree lower bound. That's clearly an upper bound for all of these. Make sense?
Yes.
Okay.
I think I didn't have the right definition of total space.
Yeah, so total space is always like, you just look at the syntactic form and just count all the variables that appear with repetition. Or count the literals with repetition. Anything else? Then let's call it a day.